Good morning, guys. Today we're going to pick up where we left off last time. We introduced some fundamental geological topics, and I promised you that we would go into some more dramatic geological events. So I'm going to start with earthquakes. And of course, if you remember back to sixth grade science, if you went to collegiate or some other earth science class, you probably learned that earthquakes involve the conversion of potential energy into kinetic energy, right? Potential energy that is stored up in the friction and the stress between two plates at a plate boundary. And then these things are going to slip past each other. And that, of course, in the process, changes that potential energy, which again is almost incalculable because we're talking about the Earth's plates here in terms of their mass. That potential energy is converted into the movement of the plates, right? Kinetic energy. And in the process, things are going to shake around a little bit. Now, sort of like the energy is incalculable, or at least it can be calculated, of course, but it's almost incomprehensible, I should say, to us. Same thing with the shaking, right? May not seem like a lot. A couple of plates slide past each other. There's some movement. But on the scale of a plate level movement, the shaking for a human and human structures is going to be of a high magnitude. No pun intended there. All right, so again, an earthquake can be strictly defined as breakage or slippage, shifting of rock at a fault. In the process, this kinetic energy that's produced is going to generate seismic waves, which are vibrations in the crust. I'll introduce a couple of terms here while we're talking about earthquakes. The point at which an earthquake originates is the focus. This can be at the surface, or more typically, it's going to be at some depth. The epicenter is the actual spot on the surface above the focus. And of course, since we live on the surface, we are more concerned about the epicenter, because that is where things are actually happening, or at least the highest impact things are going to be at this epicenter where we live on the Earth's surface. Sometimes, rarely, the epicenter and the focus are one and the same, right? If it's a very shallow surface level earthquake, but usually the earthquake is going to be at depth. Now, the amount of energy that's released is going to determine the magnitude or the amplitude of the seismic waves. And of course, magnitude is going to be a way to measure severity of an earthquake. We can look at this in a couple of different ways. We'll talk about this in a moment. And amplitude is the size of the seismic waves. They're not always going to be directly correlated, that is magnitude and amplitude, but there is a correlation for sure. But there are other factors that can affect magnitude other than just amplitude. All right, so that's a little bit of general info about earthquakes. That's going to help us to understand the next slide a little bit more. All right, so if we look at this slide here, and let me see if I can activate my pointer. Let me do the big one here, yellow. All right, so I've highlighted in yellow here the epicenter, and in red is the focus, all right? And we see these are not the same in this particular earthquake, right? We can see the actual fault line itself. I'm going to demonstrate that in, I don't know, let's try purple since there's no purple on here. There is the fault line, right? Oftentimes, we're going to be talking about a transform plate boundary, sometimes called a transform fault or a strike-slip fault. That's where a lot of earthquakes happen, but they can also happen at subduction zones, convergent plate boundaries, things like that. But especially in the U.S., most of our earthquakes that we hear about are going to happen at transform plate boundaries. All right. So again, that epicenter in yellow is on the Earth's surface, and if we go down directly below it, but at depth here, in this case yeah, I don't know, hundreds of meters. We're going to find the focus where the actual slippage occurred. All right, this obviously talks about some other things that can happen with an earthquake. For the sake of time, we're not going to go into them, but the image at the right shows the devastation that can happen at the surface. This, of course, is the earthquake that happened in Haiti in 2010. Again, this was a major earthquake, and because of the high population density of Haiti, and also the very poor living conditions and inferior structures, inferior construction, led to devastation with over 70,000 people dead and catastrophic damage across the island. All right, so that's a little bit about earthquakes there. This shows you the uh, world earthquake risk, with red being the highest risk, and then sort of a whitish blue being the lowest risk. What do you guys see on here? What does this essentially correspond to? If you said the map of the plates, which I'll show a little bit later, then you're correct. If you follow the red of earthquake risk down here along the west coast of North and South America, then you'll notice that that is going to be the plate boundary, the convergent plate boundary between the Pacific plate and the North American plate, and of course the various Caribbean and South American plates as well. I'm not going to have you guys know the various names, but there's multiple plates involved here. And again, we see here where plates are colliding or coming together, and there is subduction occurring, right? Oceanic crust underneath continental crust. Something's got to give, right? As that plate dives under the other one, it's going to scrape against it, and sometimes due to friction, they're going to get stuck, right? And then once it becomes unstuck, again, when it's stuck, that's potential energy. Once it becomes unstuck, then it's going to release all that kinetic energy as it moves down, and that's going to cause the surface to shake. It's going to send seismic waves through the lithosphere. All right, and then we also see over here an earthquake belt, right? And you may look at this one and say, well, wait a minute. Doesn't look like an oceanic plate there. Definitely some continental stuff going on. And in this case, we have still a convergent plate boundary. Remember, India, the Indian subcontinent, and its plate are slamming into the Asian or Eurasian plate. And since they're both continental crust, one is not giving way to the other. And what do you think happens there? All right, if you said that if they're equal density and one will not go underneath the other, then they're going to rise up. And of course, that is the case. What mountain range do we have here going across India and southern parts of the Asian continental plate? If you said the Himalayas, you're correct. On into Iran and Turkey and the mountain ranges associated with those countries as well. All right, so again, another example of a convergent plate boundary, but slightly different. And we see lots of earthquakes there. All right, so remember, what do we call this region along the Pacific? Here we're in the Eastern Pacific. And then if you continue the map around to its spherical continuity, then the Western Pacific forms a circle with the Eastern Pacific. And of course, we call that the Ring of Fire. Also, the Ring of Earthquakes, if you will. All right, in the U.S., this is a great example of how earthquakes work. In addition to convergent plate boundaries, we see some examples of faults and earthquakes at transform boundaries as well, here in California and on the West Coast. And of course, since this is where there's a plate boundary, this is an active coastal margin, right? Here in the west coast of the U.S., we see a lot more red and orange over there. We go over to the eastern U.S., the east coast, and we don't see much red and orange. That's because it's a passive margin. the plate boundary is where? The plate boundary for the eastern U.S., or for the plate on which the eastern U.S. sits. It's all the North American plate. This is, again, the western side of the North American plate. The eastern side is in the middle of the Atlantic, right? The Mid-Atlantic Ridge. So way away from the coastline. So that means our coastline is a passive plate boundary. All right. Excuse me. In terms of dramatic geological events or events related to geology, in addition to earthquakes, one related phenomenon is the tsunami, right? Now, earthquakes aren't the only things that can generate tsunamis, but they are the primary thing that does. And of course, they also are going to release, in most cases, the most devastating tsunamis. Remember, a tsunami is going to be a large ocean wave, and it is only large once it gets into shallow water, at least in terms of its amplitude, right? It has a very long wavelength, but in the middle of the ocean, it can be only centimeters in terms of its height, but very long wavelength. So that when it does reach a shallow area and the wavelength starts to be compressed as it drags along the bottom, that's going to create extreme heights relative to that extreme wavelength. And this is why they get so high as they reach the shore. Again, this can be caused by earthquakes. It can be caused by volcanic eruptions underwater. It can also be caused by underwater landslides. Anything that causes the ocean floor to move, rise, or drop suddenly. And again, it may not seem like much. The earthquake itself, can shift, even several hundred meters, but that energy that's released is deceptively large. And again, just a little bit of movement in the Earth's plates goes a long way, right? And what happens here is the water is displaced. Think about dropping a rock into the water and what that does in terms of that little small scale tub of water, right? It's going to create those ripples, the wave, the sloshing. If we were to move the Earth's crust and displace the water in a similar fashion, at that scale, it can produce some crazy, large waves in terms of wavelength. They can travel several hundred miles per hour. And again, once they reach the shoreline into the shallow area and they start to shoal, then they're going to increase in height. In December 2004, we had the Indian Ocean tsunami. And this is the most devastating tsunami in our lifetimes, most of us anyways. And it came from a magnitude 9.15 earthquake. And this led to 31-meter waves at the shore, over 100 feet, right? Now, in 2011, we had a tsunami in Japan that wasn't quite as large. The earthquake wasn't as large, but it hit an area of much more developed population, and it affected the nuclear reactors at Fukushima. So we'll talk about nuclear waste, and we've already started talking about nuclear energy a little bit. But this is, again, one example of the impact of nuclear energy on the environment. So again, these two examples illustrate how devastating tsunamis can be. So it's very important that we are able to we can't prevent them, right? But at least try to detect them. If nothing else, to save human lives, obviously. We do have a tsunami warning system set up, early warning system, and it's a series of buoys in the open ocean that can detect micro-scale changes in sea surface height. So again, the waves can be centimeters difference than normal, but that can be detected in terms of the average wave state. And when that is detected, they can give warning, even though it's traveling hundreds of miles per hour. They still can give warning on the other side of the ocean basin. Obviously, there's also seismographs that detect the earthquake, so you already have an idea that something could be happening, right? But you don't necessarily know the direction of which the tsunami was propagated. Again, these are important technological advancements. Here's a look at that Indian Ocean tsunami of 2004. This was a Christmas Day tsunami. Big news when you guys were infants, most of you. So again, I can remember this clearly. Very devastating. Hundreds of thousands of lives lost. Lots of damage to Thailand, India. Some islands were completely swamped, and of course, Indonesia, Sumatra, Java, and other islands. And this just again shows you how that wave is generated here in the bottom left at a fault. An earthquake occurs, and that little bit of slippage, it may not be a lot, is enough to displace the water upward and outward. And of course, that's not so much a problem until that really large scale wave reaches shallow water. And then again, if you take a look here, that really long wavelength that contains that energy is compressed together. So you see the wavelength getting shorter, shorter, shorter. And what must happen at that point is the wave height must get higher and higher and higher until we get over here, and it can be hundreds of feet high. Look at these high-rise buildings here. It's pretty terrifying, honestly. But again, with early warning systems and tsunami sirens that are connected, there have been some very successful cases of lives saved. All right, this shows you a cool satellite image that shows the before and after of that Christmas tsunami in December 2004. All right, just in Indonesia alone, which this is a picture of Indonesia, 168,000 people died. Now, that's in Indonesia alone, plus Thailand, plus India, plus the islands in the Indian Ocean. This is Banda Aceh, which was the first and most heavily impacted area, the closest populated center to the epicenter of the earthquake. All right, and again, it shows you before on June 23rd, 2004, what it looked like, and then after on December 28th, 2004, in terms of the destruction. All right. So now we're going to shift gears. We've talked a little bit about volcanoes. Again, I can't go into too much. This isn't a course in volcanology, but you get the idea in terms of them producing lava from magma. We've talked about earthquakes, tsunamis. Now we got to go into some other earth science. This is considered by most students to be a little more tedious. All right, this is going to be mineralogy and, looking at the rocks that are involved in geological processes. All right, so there's a difference between a mineral and a rock. I actually had a nice video. I'll let you guys watch that on your own here. All right, and we'll see if it works. Great. If for some reason the link is dead, then don't worry about it. But for the sake of time, I'm just going to go ahead and explain. So a mineral is going to be a pure, naturally occurring chemical compound. So you have a repeating molecular structure, right? It's a chemical compound that exists as a crystalline solid. So it has to be natural, right? It has to have crystals, be crystalline. It has to be a solid. And it has to have, again, I don't want to use the word pure, but a definite chemical composition, right? A mineral itself, if you take any chunk from within the mineral, it's going to be the same. That's not the case with a rock. A rock is going to be also solid, and also much of it is going to be crystalline and naturally occurring. However, it's going to be a combination of one or more minerals. So if you take any various chunk of that rock, it may be a little different because it may contain different amounts of the various minerals that make it up. So that's the difference between a rock and a mineral. Well, basic earth science there. All right, the Earth's crust itself, overall, is what we're really concerned about. Remember, the Earth's crust is the upper part of the lithosphere. It's the part of the tectonic plates that we are on. So obviously, we're going to be most concerned with it. The Earth's crust, as you can see, is only a thin skin, but it's where most of the geological processes that we know occur. And because of that, we want to take a look at it in depth. All right, so about half of the Earth's crust is made up of this um, mineral called feldspar. Feldspar. It's a mineral that's comprised primarily of silicon and oxygen, which makes it a silicate. SO, various combinations of S and O. Another important component of the Earth's crust is quartz. And if you look at the image down in the bottom right, we see that the various feldspars, so we have, and we're not going to, you don't even know plagioclase versus potassium feldspars, but that's over half, right? About 51%. And then the quartz is about 12%, and then things kind of dwindle off from there, right? There's other things that make up the Earth's crust, but feldspar and quartz are the two main ones. And quartz also has a lot of silicon and oxygen, and as you may guess, because of that, since these are the two primary components, oxygen and silicon are going to be the two primary elements. They're going to be found in the Earth's crust. They account by themselves for about 3/4 of the Earth's crust. And then you have some other metals sprinkled in here, right? Not a lot of metals, not a lot of heavy stuff. The light stuff kind of floats to the top, if you will, as the Earth is formed. The heavy stuff is deep, right? And that's most of the Earth. Remember, the Earth is a sphere, and we're talking volume here. So the core and parts of the mantle, and mantle, of course, is most of the Earth's volume. But because of that, there's so much else underneath the surface. Iron is actually the main element in the entire Earth, about 35%. Oxygen, still has, a heavy presence. No pun intended there, because it's not really that heavy. And then silicon and some other metals make up the rest. All right. So don't get the minerals confused with the actual elements. The elements are going to combine together to make up the minerals down here, right? But don't get them confused. All right, so this should be a little bit of review from 6th grade. The three major types of rocks, all right? Again, we're not going to go in depth into minerals. We're going to go a little bit more into rocks, since again, rocks are going to be eroded and erupted, and other processes are going to affect them. The first major type of rock is sedimentary, and this may jog your memory in terms of the other two, but we'll get to them in a second. So sedimentary rock. Again, sediment is different than sedimentary rock, right? Sediment is going to be pieces of eroded rocks, or in some cases, plant and animal remains. And it's going to collect, and it's not a rock yet because it hasn't been consolidated. But once this sediment is eroded, or weathered, I should say, remember those terms are different. Once it's weathered, if it's transported by water, wind, or gravity, then we consider that erosion. Then it's going to be taken somewhere else and eventually deposited. All right, in this depositional environment, the sediment is going to accumulate into layers upon layers. And eventually, as it gets buried and buried and buried, the pressure and also eventually the heat of being buried deeper in the Earth's crust, those two things are going to combine to compact and consolidate that sediment into a rock. And if it's really sandy sediment, you can probably guess that it's going to be consolidated and compacted into sandstone. If it's going to be more fine-grained, sort of silt or mud, if you will, then it could be compacted into this rock called shale. It has a lot of biological organisms, calcium carbonate shells, and things like that. You can get limestone, and then a couple of special sort of sedimentary rocks, if you will, or well, a special sedimentary rock that has a couple of different forms is coal, right? Coal is going to be the fossilized plant and animal remains, not the mineral shells, but the actual organic material. And if that gets compacted and subjected to heat and pressure, it can form this very energy-rich, condensed sedimentary rock that we call coal. And we'll learn later on there's different types of coal. This slide mentions lignite, which is brown coal, and bitumen or bituminous coal, which is black. All right, here's the other two types of rock. You probably already remembered these. Maybe you did, maybe you didn't. But igneous rock. Igneous rock forms below or at the Earth's surface from magma. Again, this means that the magma is going to cool and form either granite or basalt, depending on whether we're talking about an eruption or solidification of oceanic crust, or in the case of basalt, right, or continental crust in the case of granite. Again, this rock can form either through eruptions of lava, in which case, it's going to happen at the surface, or sometimes that magma solidifies or hardens before it reaches the Earth's surface. And that's going to mean it's going to have a slightly different chemical or physical arrangement anyways. It may have the same chemical composition, but things are a little different when it's formed below the Earth's surface. All right. And then finally, we have metamorphic rock. Metamorphic rock is when some of that sedimentary or igneous rock is going to be subjected to even greater heat and high pressure, or in some cases chemically active fluids, and that's going to change the rock, right? It's going to change it from one thing to the other. Let's just say that lignite, that brown coal, is subjected to even more intense heat and pressure, and it's going to be, again, compacted, and all that energy in those chemical bonds is going to be forced together a little bit tighter, right? That's when you get the highest quality coal, a metamorphic coal called anthracite. Let's just say, I don't know, that some of that shale is going to be compacted even more and subjected to high temperature and pressures. Then you get slate from the shale. And finally, what if that limestone? You've probably seen limestone before. It's kind of porous, crumbly a little bit, jagged, right? Not real regular. If you take that limestone that includes a lot of, calcium carbonate shells of little organisms, right? And you compact that and bury it and subject it to high heat and high pressure, you actually get marble from that. And you've probably all seen marble before. Obviously it's prized for its beauty and for its regularity. And that's, again, going to simply be limestone that's been metamorphosed into a metamorphic rock. So rocks are going to cycle back and forth among these three different types, right? Metamorphic, igneous, and sedimentary. And this happens over millions of years, right? The processes that are going to be causing this are erosion, melting, metamorphism. Out of the Earth's cycles, for example, the hydrologic cycle, the water cycle. We could also look at biological cycles. Out of all the Earth cycles, the rock cycle is the slowest, right? Makes sense. Talking geologic time here, millions of years. All right, so this is the last slide. Again, I accidentally skipped over it, but I just wanted to illustrate here. Again, you may need to zoom in on your screen. Hopefully you can see it, all this. There is a lot going on here. And I'm going to see if I can get my pointer active. I got my highlighter active here. That's okay. Don't need the pointer right now. Just kind of follow along with my cursor. again, you see here 3 different cycles. So 1, 2, and then 3. It's a terrible 3. But these are the three different ones we just talked about: sedimentary, igneous, and metamorphic. Gives you some examples of each of those 3. We've already mentioned those examples, but nonetheless, it's kind of interesting to take a look at these. What we're seeing here is arrows between the different cycles, and we see that you can have a direct circle between the 3 cycles, right? Igneous rock can be weathered, then eroded and transported before it's deposited. So those 4 green rectangles there. And when it's finally deposited, it can become sedimentary rock, right? So you have sediments of igneous rock. We see there's an arrow that kind of shortcuts from metamorphic to weathering. So metamorphic rock can also be weathered. And technically, you can weather sedimentary rock and then redeposit it. Sometimes it's something else. So there should be an arrow from here, from here to here as well, if you want to get technical about it. And again, once it's deposited and subjected to, enough pressure to compact it, if it gets buried further and further into the Earth's surface, it can metamorphose and change. So sandstone, can obviously be changed into various types of metamorphic rock, quartzite, things like that. Limestone as well. We see also igneous rock that was erupted or solidified underground can be subjected to more heat and pressure and change form into metamorphic rock. So again, we see that each of these has arrows that kind of shortcut from one to the other. And then finally, if the metamorphic rock is melted, it becomes magma and can be erupted or cool underneath the Earth's surface into igneous rock. Technically, the same thing can happen to sedimentary rock before it's metamorphosed. So all of these things can be connected to the other to produce this rock cycle that is a little more complicated than it looks initially, but it all makes sense when you think about it. All right, that's it for today, guys. We'll pick up next time with a little more earth science, but don't want to give you guys too many notes, in Zoom format virtually. If you guys have any questions, just shoot me an email or comment on the Google Classroom post, and I'll see you guys next time. Oops. This will be our last slide we look at, and actually this one is not the last, but I just skipped the last one. Let me see if I can go back. All right, so I'm just going to stop this.